Bismillahirrahmanirrahim. Assalamu alaikum, dear students. We are now starting the first lecture for our week number 9 for the course of communication systems. In our last lecture, we talked about random variables and we discussed that the mathematical description of random variable is PDF or PMF, depending on whether it's continuous random variable or discrete random variable. Alternatively, we can also represent the random variable by using its CDF, which is valid for both continuous as well as discrete random variables. So basically these PDF, PMF and CDF, they provide the complete description of random variable. So all types of information related to random variables that can be drawn from these PDFs and CDFs. However, in most cases we do not need to have the complete description. Rather, we study the behavior of the random variable on the basis of its statistical averages. So basically the statistical behavior is generally described by some numbers which we classify as the statistical averages. So in most cases we try to identify these averages for different types of random variables. Although there are number of random variables, there are number of statistical averages that can be used to draw useful conclusions related to the random variables. However, for communication purposes, in most cases we are interested in two types of random variable. One is mean and second is variance. However, there are others as well, and some of them would be discussed in this lecture. So we start our discussion with describing mean. We know that mean is actually the average value of the random variable. So if we calculate the overall average or of the random variable that is represented by its mean, typically we call it m of x. So we should realize that this mean is a constant number which is calculated by summing the values of x weighted by their respective probabilities. With the large number of experiments, typically this mean value represents the experimental average of the random variable. That's why we sometimes call it expected value of x, which is written as e of x, or sometimes we call it x bar. This is the notation that we use to represent the expected value. This e of something is actually named as expectation operator in probability theory. Similarly, there is another statistical average that we use which is named as movement, and there are number of movements that are related to the random variable. So typically nth movement of the random variable is actually average value of the random variable, but average value to that particular power of the random variable. So actually nth movement is average of nth power of the random variable. That means the second movement is actually average value of x raised to power 2, third movement is expected value of x raised to power 3, and so on. So therefore we can say that the nth movement is actually expected value of x raised to power n. That is, this is expected value of x raised to power n. So we can easily see that the first movement is actually mean value of the random variable. You can see that first movement means the expected value of x, which is the mean value. Similarly, second movement means the expected value of x square. So this gives us the mean square value of the random variable. Similarly, third movement and fourth movement, they also convey good information related to random variables. Another important statistical average is variance. Variance is represented as sigma x square. Variance is basically measure of dispersion of a random variable. So it shows that how the random variable is spread around around its mean value. So basically its expected value around the mean. So expected value of x minus mx square. So this is the expected value of this expression, that how far is x with respect to mx, which is the mean value. However, for calculation purposes, another form of this formula is more commonly used, which is written as this formula e of x square, which is actually second movement, minus e of x whole square, which is square of the first movement or mean value, e of x whole square. So this is the more commonly used formula to calculate variance of a random variable. Another statistical average is standard deviation, which is actually square root, actually positive square root of the variance. So this standard deviation can be written as square root of this formula which I mentioned for variance. You can see that for all those averages we have used this expectation operator in defining all those averages. So this expectation operator has certain properties. One of the important property that I want to highlight at this stage is that this expectation operator is a linear operator. So it satisfies the property of all linear operators. So if alpha and beta, they are constants, in that case expectation of this alpha x plus beta, it can be distributed to both of them, and alpha being constant can be taken out of this expectation. So this expected value of alpha x plus beta can be written as alpha into expected value of x plus beta. So by virtue of its linearity, we can use this distribution. The question here, how can we calculate this expectation, or how can we calculate all these statistical averages? So there is a standard relationship in calculating the averages of random variables. So for mean, which is actually expected value of random variable, you can see that if you want to calculate mean, what we need to do, we need to multiply individual values of the random variable with its relevant probabilities. P of x shows the probability mass function, because this is for discrete random variable, and then we sum them together. So this is how we calculate the expected value for discrete random variable. Similarly, if it's a continuous random variable, so we have to multiply this x with the PDF. You can see that the PMF is now replaced by PDF, and this summation would be replaced by integration, because of the nature of random variable is continuous. So you can see that for discrete random variable you have to sum, and for continuous random variable you have to integrate over all possible values of the random variable. Similarly, for nth moment, e of x raised to power n, the similar formula is applicable. So you have to multiply x raised to power n, because now we are calculating the expected value of x raised to power n. So whatever expected value is needed, we have to multiply that with the PMF of the random variable and then sum them together. Similarly, if we are talking about a continuous random variable, then x raised to power n would be multiplied by the PDF of the random variable and then integrated over the entire range of the random variable. So this is how we calculate movements for continuous random variables. Variance, of course, variance can be calculated by integration or summation formula, as I indicated here, by using this expectation value. So expectation, so you can multiply this x minus e of x whole square by the PDF or PMF, depending on whether that random variable is continuous or discrete, and then respectively you can integrate or sum all the possible values of random variable. So you can calculate variance by using this similar relationship as I mentioned earlier, but practically most commonly used relationship is this one. So we calculate second movement and first movement and then from second and first movement we can calculate the variance of random variable. So in order to illustrate how we calculate these statistical averages, let me take a simple problem of a continuous random variable, and we want to find mean and the standard deviation. So we have a random variable x. Of course, as it's continuous random variable, it should be defined by its PDF. So this PDF is given here. Fx of x is 2 of x when the x is between 0 and 1, and for all other values this PDF is 0. So let us start calculating the statistical averages for this particular random variable which is given in this problem. So mean is calculated, m of x is expected value of x. So you can see that in order to calculate the mean, we have to multiply x with the PDF of the random variable and integrate it over the entire range of the random variable. However, from the PDF description we can see that this PDF exists only a specific range of values of x, which is from 0 and 1, and for all other values, so the PDF is 0. So therefore we do not need this infinity, minus infinity to plus infinity limit in this case. Rather we can restrict our calculation at this given range, which is 0 to 1. So for this this random variable x is mentioned here. The PDF for the given range fx of x has the value 2x, so which is given here, 2x dx. Therefore this mean value can be represented as 2 times this integral of x square. 2 being constant has been taken out of the integral. So if we integrate x square, so it will be x cubed by 3 with the limit 0 to 1. And if we apply those limits, 1 being upper limit and 0 being lower limit, we applied those limits and simplify, we would see that the mean of the random variable comes out to be 2 by 3. Similarly, we need to find standard deviation, but in order to find standard deviation we need to calculate variance first, and before calculating variance we need to have second movement. So in order to calculate standard deviation, the first step is to calculate second movement of the random variable. So now we calculate second movement of the random variable, which is given by e of x square. So as I described earlier, the second movement is given by multiplying this x square by this PDF of the random variable and integrating over the given range. However, as the random variable exists for a specific range of the random variable, so we can restrict our integration at the given range, which is 0 to 1. And at this point we can substitute value of PDF, which is 2x, and with multiply with x square. So this becomes 2 into integral of x cube with a limit 0 to 1. So if we integrate x cube, it will be x raised to power 4 upon 4. So integration of x cube would be x raised to power 4 upon 4 with limit from 0 to 1. And if we substitute limit, this 2 would cancel out with 4, giving 2, so I can write it as 1 upon 2. And if we substitute the limits, it will be 1 raised to power 4 minus 0 raised to power 4. And after simplification you would see that the second movement comes out to be 1 upon 2. Now we calculate the variance. As I said, variance can be calculated by first and second movements. So by simply subtracting the square of the first movement from second movement. So variance sigma x square is actually e of x square, which is second movement, minus the first movement, which is the mean value mx raised to power 2. as we have calculated both first and second movements, we can simply substitute values here. So second movement is 1 upon 2, first movement is 2 by 3 raised to power 2. So if we simplify this, you can see that the variance comes out to be 1 over 18. From variance, it is very easy to calculate standard deviation, because standard deviation is actually defined as the square root of the variance. So if we take square root of 1 by 18, so it comes out to be 1 upon 3 under root 2. And you should know that this standard deviation is always taken as a positive quantity. It cannot be negative. So this is how we can calculate variance, different statistical averages that are commonly used in our analysis. So at this stage, I would try to provide a brief introduction to some of the commonly used random variables in communication systems. Although it is not the complete list, these are just examples of some of the random variables. There are other variables that are also used in different areas of communication system as well. So first is the Poisson random variable. Poisson random variable actually is a discrete random variable which takes values starting from 0, 1, 2 and up to infinity. It can take infinite values. It has a parameter lambda, which is a positive number. Lambda is given here. The probability mass function of this Poisson random variable is defined by this relationship. So x can take the probability of x taking the value I. So ith number of occurrences, it can be given by this formula, e raised to power minus lambda raised to power I upon I factorial. If we calculate average of this random variable, you would see that the average comes out to be lambda. Further, the variance also comes out to be lambda for this a particular type of random variable. Some of the common examples that phenomena that obey this Poisson distribution law are listed here. For example, the number of misprints that occur in a book, they can be approximated by Poisson random variable. Similarly, number of wrong telephone numbers that are dialed in a day, they also follow this Poisson random variable. The number of transistors that fail on the first day of their use, that number also gives can be approximated by this Poisson distribution. And the number of customers entering in any post office or any bank, they can also be approximated by this Poisson distribution. Another random variable is named as uniform random variable. So it has a uniform probability density function in a certain interval given by alpha to beta. So for a given interval, it has a constant PDF which is given by 1 over beta minus alpha, and for all other values this PDF turns out to be 0. So it has a equal probability for all values of probability of occurrence for all values of x. The example of this uniform random variable can be seen by observing the phase angle received through wireless environment, because that phase angle generally is distributed using a uniform distribution in the range 0 to 2 pi. The expected value of this uniform random variable is given by alpha plus beta by 2. The variance of x can be given by beta minus alpha square over 12, and this can be calculated by the procedure that I shared earlier in the problem. Another one of the important random variable in communication systems, or perhaps the most encountered random variable, is Gaussian random variable or normal random variable. The Gaussian random variable follows the Gaussian curve, which is which has certain mean mu, and variance sigma square. So our random variable x have the Gaussian distribution with two parameters, mu and sigma square. If their distribution is defined by this value, which is fx is equal to 1 upon under root 2 pi sigma e raised to power minus x minus mu square upon sigma square. The mean, as I mentioned, is mu, variance is sigma square. However, sometimes we make another substitution, that z can be used to substitute this x minus mu upon sigma. So this z is also normal random variable, but it has a standard property that it has a mean 0 and variance equal to 1. So whenever Gaussian random variable is defined by this mean with this z that is having 0 mean and variance 1, it is said to be standard normal distribution, and most of the mathematical results, they are calculated on the basis of this standard normal distribution of random variable. The common example of this Gaussian distribution in communication system is that of noise. The thermal noise that occur in almost all type of communication systems, they that follows Gaussian distribution with 0 mean. However, the variance depends on the noise power. So variance is actually equal to the noise power that occurs in that particular type of system. Another random variable is named as exponential random variable. The exponential random variable is also a continuous random variable like uniform and Gaussian distributions, but it has this probability density function which depends on a parameter alpha, and it follows this exponential distribution. So it's given by lambda e raised to power minus lambda x, and it exists only for positive values of x. You can see that the existence is for all positive values of x, and for negative values the exponential random variable is 0. The mean and the variance of this exponential random variables are given by 1 upon lambda and 1 upon lambda square. You can calculate these means and variance by using the relationships that I mentioned earlier while we were solving the problem. A common example in communication system is time duration between two consecutive calls, which is sometimes named as inter-arrival time. Typically, that inter-arrival time can be approximated by exponential distribution in practical scenarios. So these were some commonly used random variables that we frequently encounter when we analyze different phenomena in communication systems. However, I must mention that these are not this is not the complete list of the random variable that we use in communication systems. There are other important random variable which are also used in variety of different communication systems, and hopefully you will be encountering those random variable in different scenarios as well. For example, Rayleigh random variable and Gaussian random variable and binomial random variable, they are one of the commonly used are among the commonly used random variables that we encounter in analysis of communication systems. Okay, so now as we have discussed different statistical averages related to the random variables, so let us try to conclude our discussion by taking another perspective related to these random variables. As for the case of probability theory that we were discussing in last week, there are possibility of defining more than one random variables for certain random experiment. So if we have, say for example, two random variable x and y, so in that case we can also define there a joint distribution. We have previously discussed the probability density function of a random variable, which was the distribution of one single random variable. Similarly, we can have joint distribution, which is actually giving you the joint probabilities of occurrence of x and y, which is given by this pxy, x comma y. If you need to find a probability related to certain event in this joint distribution case, in that case you would be needing the range of values of x as well as range of values of y, because for continuous random variables we know that we need to have the ranges where you want to find the probability. So so if we have this range of values of x and y given by a to b for x and c to d for y, in that case we can easily calculate the probability corresponding to this event by integrating with respect to both x and y. So that's why we will be needing double integration if we have joint distribution for two random variables. So you have to integrate first with respect to x for the given ranges of x, and then you have to integrate with respect to y for the given values of y, although the order of integration is not important in this particular case. Similarly, if you have more than two random variables, like three random variables, in that case the probability will be calculated by triple integration, and so on. As we discussed previously for the case of probabilities of different events, similarly if we have random variables x and y, we can see that whether they are statistically independent or not by using their PDFs. So if this joint PDF is equal to the product of their individual PDFs, in that case these x and y, they are called statistically independent. So this is the condition of statistically independent random variables, and you can see that this is the similar condition that we also discussed in the probability theory, where the joint probability of two random variables should be equal to the product of individual probabilities when the events are independent. So similar result is observable in this case of random variable as well. As we have defined the joint distribution, which gives the joint probabilities for the event, we can also calculate the conditional density function for the random variable, and you can see that the conditional density function is defined in similar fashion as we defined the conditional probabilities of the events. So this conditional density function, which is written by px given y, x given y, is the distribution, is giving you the distribution of x when you know the value of y. As it has the same concept as we discussed for the case of probabilities of events, that actually this px given y is distribution of x when you know the value of y. So mathematically this p of x given y is defined by this joint distribution divided by the PDF of y. Moreover, the standard Bayes theorem, which we discussed for the probability of events, is also applicable for the conditional distributions for the random variable. So where needed, you can use the same Bayes theorem to relate the conditional distribution of random variables as well. From conditional distribution or joint distribution, we can also calculate the individual probabilities of random variables, which are named as marginal distributions. So what are the marginal distribution? Marginal distribution, for example, if you have a joint distribution P of x given y and you want to calculate the individual distribution of x only, so what you need to do, you have to integrate this joint distribution with respect to y. You can see that this is integrated with respect to y, and of course we need single integration. So this integration results in the marginal distribution of x only. Similarly, you can calculate this individual distribution of x from the conditional distribution of x and y. So if you have conditional distribution of x given y, and if you integrate it with respect to y by multiplying it with this probability function distribution of y, you will get the distribution of x. You can see that this relationship comes directly from this definition of a conditional distribution by simply multiplying this px given y with py. So this pxy can be related to conditional distribution, so which has been done in this relationship here. Similarly, if you have joint distribution of x and y and you want to find distribution of y, so in that case you have to integrate this distribution with respect to x. So if you integrate the entire distribution for all possible values of x, so you will end up with the marginal distribution of y, which is given by py. Similarly, it can be calculated from the conditional distribution of y as well. Let us take a simple problem. So joint PDF of two noise voltages. So there are two voltages here for which the joint distribution is given by this expression 1 upon 2 pi e raised to power minus y square xy plus x square by 2, where x and y both exist in the infinite range from minus infinity to plus infinity. So this joint distribution is given. If I ask you to find individual distributions or marginal distributions of x and y, so we can do it by simply integrating with respect to the appropriate variable. So if we want to find the marginal distribution of x alone, that is px of x, so we have to integrate this joint distribution with respect to y. And of course the range of y is from minus infinity to plus infinity, so we have to integrate to the entire range. And if we simplify this integral, so you would see that by using the standard relationship of integrals, this distribution comes out to be 1 upon 2 under root pi e raised to power minus x square by 4. Similarly, if you want to calculate the marginal distribution of y, in that case you have to integrate this joint distribution, which is given by 1 upon 2 pi e raised to power minus y square minus xy plus x square with respect to x. So if we integrate it with the entire range of x from minus infinity to plus infinity, we will get the value, the distribution for y, which comes out to be 1 upon 2 pi e raised to power minus y square by 2. If I ask you to check whether x and y are independent or not, in that case we can simply check these by multiplying these two marginal distributions. So if you multiply this thing with this marginal distribution of y and we compare it with this joint distribution, you will see that the product is not equal to this joint distribution. So this is not equal here. So in that case, since the product is not equal, we conclude that x and y are not independent because the product is not equal to the joint distribution. So if they are not independent, we can easily find the conditional PDFs by simply dividing this joint distribution by the relevant marginal distribution. So this joint distribution, conditional distribution of y given x can be calculated by dividing this joint distribution with p of x, which comes out to be this value. Similarly, the conditional distribution of x given y can be calculated by dividing this joint distribution by the distribution of y, which comes out to be value here. So you can see that if we have more than one random variable, in that case we can also calculate their independence and dependence in similar fashion as we have done it in the probability theory for the case of different events. As I mentioned that in most cases we are interested in calculating the expected values of the random variable. So if you have functions of two random variables, in that case you can also find the expected value, which is called multivariate expectation, in the similar fashion as I explained before for the case of single random variable. So if you want to find the expected value of a function of two random variables, for example function is represented by g, in that case you have to multiply it with the joint distribution of x and y and then integrate it with respect to both random variables. Recall that in case of single random variable, we discussed that whatever function you are calculating, expectation of whatever function you are calculating, you have to multiply with the PDF and then integrate. The same fashion is here. The only difference is that now we are talking about the joint distribution. So if you have a function of two random variables, you have to multiply it by the joint distribution and integrate with respect to both random variables. Definitely you will be needing double integration for that case. And as we know that if the random variables are independent, their probabilities or their distributions are independent. So for the case of independent only, this expected value of x into y can also be written as the product of their individual values, e of x into e of y. But you should note that this relationship is only true for the case of independence. If the variables, random variable x and y are independent, if they are dependent, in that case this relationship is not true. One of the common case that we encounter in communication system is sum of two random variables. If for example z is a random variable which comes out to be sum of two random variable x and y, and if we want to find the mean and variance of z, in that case the mean of z is calculated by simply adding the means of x and y. So by virtue of the linear operation because expectation is a linear operator, so we can simply add them together. So mean of z is actually mean of x plus mean of y. However, if you calculate the variance has rather complicated form, which is given by this expression. But if x and y are independent, so this is the relationship when you have both random variable which are independent. So this e of xy comes out to be equal to mx into my. So this goes off. So eventually the variance of z can be written as variance of x plus variance of y. But you should know that this relationship holds only if x and y are independent, and it's not valid if they depend on each other. So for independent random variables, the mean of sum is actually variance of sum is actually equal to the sum of their individual variances. So this was a brief discussion related to the joint distribution and conditional distribution and multivariate expectation of more than one random variables. So I would conclude the discussion on random variables at this stage. Inshallah, in next lecture we'll be starting the discussion on random processes. Thank you all.